Attendees are in listen-only mode.
Okay, I want to thank everyone for joining us this morning for our Build Your Simulation IQ on Simulation Composite Analysis. Dean Rose will be hosting the session going over cohesive modeling. So we're just going to wait another minute or two here and let people filter in, but we should be starting in the next minute or so. Thanks.
All right, so it's 2 minutes after. We'll go ahead and get started. And I am Dean Rose. I'm a support specialist here at Autodesk. And also with me, I have Rick Delgarno, who's a technical consultant here at Autodesk, and we were part of the original team that helped develop some of this technology we'll be covering today as part of Firehole Composites. So we will begin the presentation now. I'll start by introducing some of the background on what a Build Your Simulation IQ webinar is. This is presented for all the simulation products we have here at Autodesk: simulation mechanical, simulation CFD, mold flow, as well as the composite products, simulation composite design and composite analysis. And we cover a variety of support topics that come into us, and we try to explain these a bit further in detail. And most recently we had a What's New in Autodesk 2015.1. This highlighted some of the new short fiber functionality that was introduced with that release. And if you are a simulation composite analysis user, I invite you to check that out and review some of that material and see if it's applicable for the analyses you're doing. I'd also like to mention you can download today's presentation on the link provided here, autodesk.box.com/ASCA5, and it'll have a PDF of the presentation material, and if there's any requests for any additional information, we'll include that in there as well. All right, cohesive modeling using simulation composite analysis. I'd like to start off with a quick poll to see how many of our attendees are performing an analysis with composite materials. And we'll go ahead and launch the poll here and give you guys a few seconds to go ahead and click if this is something you're doing. And then we'll share those results and see what kind of audience that we have today.
Okay, so it looks like we've got people voting here. Looks like the most common answer is often.
All right, great. So we have the right audience here. So we'll continue on. And first thing we're going to cover in today's presentation is when to choose cohesive elements. When do we want to incorporate cohesive elements into our finite element model, and then what kind of responses that we're looking to capture when we do this. We'll cover some of the unique challenges associated with the prediction of progressive failure and this non-smooth softening response, as well as the Autodesk tools that are provided to answer some of these challenges. And then we'll wrap things up with an example problem demonstrating the setup and execution of this type of analyses. And has anyone is anyone familiar with the cohesive elements and composite delamination? Is this something anyone has done before? We'll go ahead and launch a poll and get some feedback on that as well.
It looks like most everyone's answered here, and the common answer is I've done a few analyses.
Okay. So We see everybody has a little bit of exposure, so they've probably encountered some of the issues that we're going to touch on today. All right, so let's start off by when to choose cohesive elements. We're going to be using cohesive elements in our simulations when we're looking at a specific behavior. We're typically looking to simulate an area where we have two materials being pulled apart. A common event where this would occur would be delamination. Specific to composites, this is a common area of interest when looking to capture the true composite response. Composite analysis is primarily used to capture progressive failure behavior, and part of accurately identifying the various constituent failure mechanisms in the ply, we also need to evaluate the consequences of softening the response between the plies. And a few other areas would be an adhesive joint and fracture at a bonded interface. And these are a few areas where cohesive simulation would provide some benefit. So now that we know when we would use a cohesive element, let's look at what we're trying to capture. And I have a short video here that I'm going to play, and I'm just going to speak over it as we demonstrate a little bit of the response. This is a dual cantilever beam that we're loading. And we're going to be looking in the abacus environment, and we're going to be displaying some of the state variable outputs that are available with simulation composite analysis. And this is a SDV1, which is a damage state variable. And we're seeing the part being loaded. The two plies are being pulled apart, and we see that red area, which is a cohesive layer. And we see those elements beginning to experience some damage as they're being loaded. We'll go ahead and look at some of the other state variables that are specific to composite or cohesive results, and we're going to isolate this cohesive layer. And so what we're doing right now is isolating that, and now we view this cohesive layer. And we see a blue area, and that's indicated undamaged. And then we see that green area, that's a crack front that's propagating through the sample as it's being loaded. And that's indicating to us that these elements that are highlighted in green are experiencing some sort of damage as they're being loaded. And then we also have the red area, and that red area is showing us that these elements have been completely damaged. They're no longer contributing any load carrying capability, and the stiffness in those elements has been reduced to 0. So when we're doing this analysis, we're looking to capture some of the material softening response, and we're identifying areas where we're experiencing damage in that cohesive zone, and also looking at how that damage propagates through the simulation. All right. When doing cohesive type analyses, we're going to encounter some challenges along the way. When doing an implicit analysis, there are some real obstacles that we have to overcome. One of these is convergence. The softening response that we're looking to capture at both the material and structural levels is going to cause some severe convergence difficulties. This is going to result in early termination of the simulation simply because a converged equilibrium could not be obtained. And we'll cover a little bit more about this and how Autodesk Simulation Composite Analysis addresses this challenge specifically. And the next challenge users encounter a lot of the time is mesh dependency. When determining cohesive material properties, it's important to recognize the fact that predicted cohesive behavior is mesh dependent. So if you use a consistent set of cohesive properties across a wide range of cohesive mesh densities, you can get a variance of predicted delamination responses. So remember, if you change the mesh, you're going to have to recalibrate these cohesive properties. And then lastly, we get a lot of questions on where to calculate or how to calculate these material properties properties and where they come from. And I'd like to just note that determining these values involves an iterative process focused on calculating the cohesive stiffness properties, calibrating the initiation strengths, and this is a pretty deep topic, and we could probably cover a webinar just on this itself. So I'd like to focus any related questions in a follow-up after this webinar. And so if you have any of those, feel free to go ahead and type those into the questions column, and we'll try to address those afterwards. All right, so we've covered a few of the challenges that we can encounter when doing this type of simulation. Now let's jump into what Autodesk is providing for you as the user. Many of you may not be familiar with the convergence enhancing capabilities included with Simulation Composite Analysis. So I'll take a minute to go over those. This Autodesk tool provides a multi-scale progressive failure enhancement for facilitating a composite simulation within other finite element codes. This provides robust convergence capabilities that you may not have seen before. And some of the supported platforms that we are in are Abacus, ANSYS, and MSC Nastran. The software works in conjunction with these FEA platforms, and in addition to providing the composite capabilities, we also offer this convergence enhancing algorithms for simulating interlaminar failure and delamination. And for the last poll today, I'd like to just ask, get a feel for what kind of FEA solvers that our viewers are using. So we can go ahead and launch the last poll of the day. And it looks like we've got some vote coming in for Abacus. All right, and it looks like everybody has chimed in. So it looks like everyone is using Abacus, but we do have some other platforms available if you're looking to do that type of analysis. And the cohesive solution is very similar to the offerings for many commercial implicit finite element codes, but our proprietary software facilitates the convergence equilibrium solutions. And this improved performance gives you a unique opportunity to study the response of not only the composite ply, but the coupled characteristics of the cohesive layers. And lastly, we have a user interface within Abacus and ANSYS that allows you to input the cohesive material properties. And along with the entries that we have inside that interface, we also have a pretty in-depth knowledge base on the online documentation that's available. It explains each entry in great detail, and we also have some tutorials available for entering that information. So a lot of information at your disposal. All right, now we're going to get into running through an example. The example that I wanted to demonstrate to you today is the dual cantilever beam, commonly known as DCB. You may hear me refer to it as that throughout the webinar. And this is a model that we use to demonstrate some of the basic principles of our approach to modeling cohesive behavior. It's just one of several methods, but we get a lot of inquiries on the setup and some of a few areas, so I'm going to highlight those. And there's a few reasons why we have this problem as a tutorial. It's a great experimental problem to use when calibrating material properties. And a few things that we have here as I'll walk you through the model setup. We have a fixed end here that's constrained, and we have two elastic ply definitions, and they are separated by a cohesive layer that's using our material model. So We're applying a displacement on each ply, one pulling it up and the other is pulling down, and that's causing some separation of mode 1 cohesive behavior in that cohesive layer. And I will jump into the Abacus environment and we'll take a look at some of the results. First we'll take a look at the setup of this particular model. And here we have the Abacus environment, and I'm going to go through the plugin that we have available for entering the cohesive material properties. And you can name your material, enter your stiffnesses, tractions, and also choose the type of damage initiation. We have maximum traction, quadratic traction available, and then the damage evolution. And we have displacement, energy, and then mixed mode power law available. So we have quite a few options here for you to choose from. You can enter these in and it'll save the material just as it normally would for any type of Abacus analysis. So you don't have to input those through the standard Abacus window. And another area that we get a lot of questions about is creating the step and the associated solution controls for those steps. And we'll switch to the step module. And for solution controls, we're going to go to Other, General Solution Controls, Edit, and we're going to select the load step. It'll give you a little warning here. We'll go ahead and click Continue. And you'll see here we have, by default, Propagate from previous step is selected. We'll want to choose Specify, and that'll give us the ability to specify these inputs. And the reason we want to do this, increasing these values will ensure that Abacus takes full advantage of the improved convergence characteristics provided by our software. And so this is listed in the tutorials. It's often a common misstep as they go through the tutorials, and we get a question from specifically new users that are new to this type of analyses. They'll get an analysis failed message, and the reason being is these values have not been changed. And so ensure that you do this as you go through. These steps are identified in I believe most of our tutorials that we have available. So just make sure you notice this and go through those changes. And if you do not, you'll likely result in a failed analysis. So these are a few of the basic setup questions that we have when using cohesive elements. And now we'll begin to look at some of the results. I went ahead and ran this earlier. This analysis takes about 10 to 12 minutes. So in order to expedite the process, we'll go ahead and look at a few of the details. So I'm going to go ahead and change the view to show the entire model. And what we see here, we have this gray area, which is the ply material that we define using an elastic material definition. And then we have the red area, which is a zero thickness cohesive layer that we've defined. And then on the bottom we have another gray area, which is an elastic ply. And you'll notice that we don't have any SDV output for this elastic material, and that is by design. You won't see that type of output unless you're using our material models. So sometimes users ask, well, where's SDV1 for this elastic material, and it won't be available. So we'll focus on the cohesive material. So I'll go ahead and highlight those elements. And this gives us the opportunity to see a few things. We'll go back to SDV1, and you'll see a 0 to 26 scale. 0 means there's no no damage that's occurred. This SDV1 is indicative of the current damage state of the element, and it is tracked from 0 to 26. We also have SDV2, which is important, and this tracks the progression of the element as it approaches damage initiation. 0 means no loads or only compressive loads are acting upon that element, and then 1 would mean that the damage initiation criterion has been satisfied, and from that point forward the stiffness will begin to be reduced. And the most important state variable we'll be looking at is SDV6, and this is what we refer to as the damage variable, and it's also identified on a scale of 0 to 1, indicating how much damage has occurred. So 0 is no damage. That would be, I'll pull up a traction separation curve here, and 0 for the value of D, this damage variable, will be at the point where the damage initiation occurs. And as we progress towards this final displacement, the damage variable will increase to a value of 1. And once that value of 1 is attained, what that means to us is that this element is fully damaged. The stiffness has been reduced, and it's no longer contributing to the load carrying capability. And we can see this from this analysis here. I will progress through the analysis, and we'll walk back through. This is the unloaded state. You can see that all the elements in the cohesive material are undamaged. SDV 6 value of 0. And as we begin to load this part and pull those two elastic plies away from each other, we see this damage begin to progress through the sample. One area that we see here is this green area, and though that value is kind of an intermediate value, and these are elements that are starting to experience damage. So they're seeing this softening response, and then we have these red elements. These are indicating that the element has been fully failed. So as we go through this, we can see that crack front propagating through the sample as it's being loaded. And ultimately, we reach the end of our prescribed displacement that we're using in our analyses. So this is great to see that localized damage areas inside your part. And one of the things I'd like to highlight when using cohesive elements is we don't want to use this technology unless we're expecting or anticipating this type of delamination cohesive behavior. This sample here is very specifically designed to highlight one mode of cohesive damage. So that's why we use the cohesive elements. But if you have a sample that you're using and you're not sure if cohesive damage is going to be occurring, you probably don't want to introduce that this cohesive technology in there. It's just not effective to set it up for your time. So try to avoid it unless you're trying to model that in your simulation. And so that's one example that we have, and it's available as a tutorial online through our Autodesk site for simulation composite analysis. And in summary, I just want to highlight a few things that we've covered today for Autodesk Simulation Composite Analysis. This provides robust convergence capabilities. It improves the convergence capabilities that you may have experienced before. And it also can make analyses possible where you didn't experience this before. I've looked through a few research papers, and they've had to use explicit technology in order to get a converged solution. So this gives us the opportunity to increase the capabilities of our implicit solvers. And now we'll jump to some question and answers. And if you feel free to ask any questions through the question dialog box, and we'll try to get to those. If we can't answer those during the presentation, we'll try to follow up directly with you. And we'll hold here for a few minutes and see if any questions come in.
Dean, it looks like we do have one question here from Adam. Adam asks, are cohesive stiffness values penalty stiffness as described in Abacus, i.e. the stiffness of the traction separation curve, or the stiffness of the bulk material, for example, the epoxy?
And I think we have someone on the call that can probably answer this question.
Yeah. Go ahead, Don.
Go ahead, Rick.
Take it, Rick.
Yeah. So the stiffness that we use in the cohesive formulation, it would be considered a penalty stiffness, and there's the equation that we kind of recommend to use. Basically, takes into consideration the stiffness of the neighboring plies, so the normal stiffness of the neighboring plies. So it'd be like E33, and then you also have a factor, a coefficient that you multiply that by. And from the research that we've done, that coefficient is usually about 50. So you take 50 times the stiffness of your neighboring composite plies, and then you divide that you divide that product by the thickness of the neighboring plies. So you take that baseline stiffness, multiply it by 50, and then you divide it by a small thickness, and you get, a bit of a penalty stiffness.
And the reason that we use that particular method for calculating the penalty stiffness for the cohesive elements is that, a penalty stiffness needs to be large, but for cohesive elements, if the penalty stiffness is too large, then our stress field at the delamination front oscillates very bad. It becomes inaccurate. And so we need a stiffness that's high enough to not allow a lot of excess compliance between the plies. We want to hold the plies together until the cohesive material fails. But at the same time, we don't want to get the stiffness so high that it causes spurious stress oscillation.
All right, great. Thanks, Don. Thanks, Rick. Adam, did that answer your question? Feel free, you can reply in there. If you have any additional questions that you'd like to know about. All right, looks like we addressed that specific question. And I'm not seeing anything else at this time, so we'll leave it open right now for people to ask questions, but I'll go over a few final details from the webinar. Again, you can download today's presentation. The PDF form of this document, it will be available inside this folder here. Again, autodesk.box.com/ASCA5. And also the webinars are recorded and they'll be put on YouTube, so you'll be able to view this webinar as well as the previous composite webinars, in addition to all the webinars we have for the simulation products. So feel free to search on YouTube for those. If you were unable to attend today, you can also get an update as we close this regarding the link for the YouTube specifically for this webinar. So you'll be receiving that email after this webinar. And I invite any of you to contact support if you have follow-up questions after the webinar, something that you didn't think of or something that may come to mind as you walk through the tutorial. Feel free to reach out to us. We're glad to answer any questions and see how people are using our product. And we'll hold for a moment, see if any other questions come in.
All right. Well, it looks like the stream of questions
All right.
has ended here. So I'd like to thank everyone for joining us today. And like Dean said, if you have any additional questions about this, don't hesitate to contact us at technical support.